Thank you so much, Manuel, and it's really a big pleasure to give a talk here. It's really nice to see you. So we're good friends in Chicago, good old times. So I'll talk about the implicit limit for the Navier-Stokes equations. I will not assume much prior knowledge about fluids equations. I hope I'll not be too how to say, obvious, but just wanted to give a rather general introduction than to talk too specialized. So first I'll introduce the Navier-Stokes and Euler equations, the classical results, then talk about the implicit limit problem. So that's the convergence of the Navier-Stokes equations to Euler equations in the Rn, so in domains without boundary, and then with boundary and verticity to some more recent results. And at the end, a bit about parental equations, time permitting. I usually prepare more transparencies than I'll cover, so that's quite optimistic what I put, but I just don't want to run out. So first I'll start with the introduction to the Euler equations. So the Euler equations are equations for the velocity and the pressure of a fluid, which is inviscid and incompressible. So U is the velocity, P is the pressure. This term represents the acceleration of a particle. So this could be viewed as a Newton law that the force acceleration is equal to force. So P represents the pressure forces, and in Euler equations there is no other forces than that. And it is known in many different spaces, but for example in a Sobolev space, L2 Sobolev space, that if a solution is in HM, where M is large enough, in particular bigger than T plus 1/2, there exists T positive depending on the initial data and on the parameters, and the unique solution, which is smooth in the spatial variable, so it remains in the same space for the Euler equations. So these are classical results. So initially it was proven by Ebin and Marsden with flow of diffeomorphisms, and then Temam with HM in Sobolev spaces by doing the energy estimates. There's also Bourguignon-Brezis. So then on the other hand, we have the Navier-Stokes equations, which take the form similar to the Euler equations, except that we also incorporate the viscous forces. And so again, U is the velocity, P is the pressure. These two terms represent the acceleration or the material derivative. And again, we have the pressure forces and the viscous forces. So again, it's a second Newton law. And the second condition is the incompressibility, which kind of helps us determine the pressure, or pressure is there to preserve the incompressibility. We can view it one way or the other. So here also we have global weak solutions, as it's well known. So for the Navier-Stokes equations, we can formally multiply them by U, just do the L2 estimate, and both terms involving both nonlinear terms are zero. So Uj, Dj, Uk, this one is zero because of the incompressibility, just integrate by parts, and pressure too. So you can integrate by parts and obtain vanishing, and we get the energy decay. And based on this, Leray proved that there exists a weak solution in the space L infinity L2, L2H1, such that the energy inequality holds. And this form of energy inequality is valid from 2 times, and it's for almost every T1 and for every T2 greater than T1, and also includes 0. So it's also true for 0, if you put 0 on both sides. So these are well-known weak solutions, and they're meant as weak solutions that satisfy the Navier-Stokes equations in a weak sense. So if you multiply or test again against the function phi, which is divergence free, that makes the pressure term go away, and then the Navier-Stokes equations are satisfied in a weak sense. And as it is well known, we don't know whether there are solutions which remain smooth for all time, even if you start with a very smooth datum. And it's also not known whether relay solutions are unique. And there's a lot of progress recently about that, so it's very nice to see. So if there is no boundary, so then the same Euler proof which gives existence as in the energy estimate proof of Teman works for the Navier-Stokes equations, and we can obtain the existence of solutions on a time interval independent of the viscosity. So the same proof as for Euler, the viscous term just we integrate by parts, and we obtain also the local solutions in HM m bigger than 1 plus d over 2. And we can also get solutions for lower smoothness of Sobolev spaces, but the solution may depend on the viscosity, also the time interval. So the basic question of the Inviscid limit is, do solutions U of the Navier-Stokes equations converge toward the solution of the Euler equations as the viscosity term goes to 0? So as viscosity goes to 0, this term is formally disappearing. So we may expect perhaps that solutions maybe converge on some time interval in some norms. So, and this is a singular limit, so it's not to full extent. The answer is not known, as I will discuss in this talk. But in some cases it's known. For instance, in the cases without boundary, and I'll show you the sketch of the proof. Okay. So again, we can, in any kind of norm, this is an interesting question. So for when the domain is without boundaries, so if omega is RD, or if it is the torus TD, and the dimension is 2, 3, there is a history of the problem, and the answer is basically yes. So first, initially, the proofs were using Helder spaces, and even in the initial paper by Abin and Marsden, they approved the Inviscid limit in this case. The simpler proof is then given by Kato, and then perhaps the best current result is by Masmoudi. So I'll mention these 2 results below. That's for the case without boundary. So the following is the version as stated by Kato. So his notation is actually quite convenient. So we'll write U for the solution of the Navier-Stokes equations and U bar for the solution of the Euler equations. So Kato proved in 1972. I must have touched some. Oh, I touched the pattern. Sorry, it took me all the way down. I have to find a place. This we did. Yeah, sorry about that. I should avoid these patterns here. But so in 1972, the Kato proved that if U naught is in HM, m greater or equal than 3 integer is divergence free, there exists a time depending on the size of the initial data, but not on the viscosity, such that U solves the equation and belongs to the space. So it's continuous in time with values in HM, and more regular in time as the regularity of the spatial variable decreases. And then in terms of the Inviscid limit, usually such kind of upper bounds are useful for Inviscid limit, and indeed, once you have uniform bounds, you can pass. And then here he proved that the limit exists strongly in HM minus 1. But there is a problem with integration by parts in HM. So if you just try to do a simple proof, as I'll show you in a moment, it does not work very well for HM. However, there is a nice proof by Masmoudi in 2007 that actually strong convergence holds also in the high space HM just by regularization. And moreover, by this paper, the convergence holds on the whole interval of existence of the Euler equations. So it's a quite satisfactory result for the domains without boundary. There's also results for rough data. So Konstantin Wood proved if you have vortex patches, there is also a vanishing viscosity limit with a weaker sharp convergence. So one can study this with high regularity or low regularity. So here is the proof of the strong convergence in L2, which is quite simple. So we take the difference of two solutions, which satisfies the equation, which is the, so here is a typo. So the difference satisfies this, which is the main part is same as the Navier Stokes, and the nonlinearity is this form V grad U bar plus U grad V. And the pressure is just a difference of two pressures. So we can test the equation by V and integrate. So same as in the energy estimates, this term leads to the derivative of the L2 norm squared. Here we can just integrate by parts and obtain the new gradient V squared. This term does not go away as it did for the basic energy inequality for the Navier-Stokes equations. So we just test it with V, we obtain this term. However, the second nonlinear term goes away because the integral of U grad V is 0. And we obtained, no, that was actually not a typo. Yes, okay, sorry. There's no viscous term in the U bar. So we write it as a nu times gradient V plus nu gradient U bar. And we estimate this just without even integrating by parts. And we can cancel the L2 norm. So just cancel it. We can omit this term. And we obtain the basic energy inequality. And we notice that this term has nu, and this term is just exponential increase. So this simple reasoning tells you that that because these terms are uniformly bounded, you can always just bound Euler solutions with constants, any kind of norm. So for high regularity initial data, which is the case if m is at least 3 integer, we obtain that the L2 norm is of nu as nu goes to 0. So it's just because of this nu here. So the solution not only converges to 0, as solution is the difference of V is the difference between the U and the Navier-Stokes equations. And in L2 norm, it goes to of nu uniformly in time. And so basic ingredients in this proof were one of the nonlinear terms went away. Then the smoothness of U bar. So everywhere where we saw any kind of norm of U bar, we could just bound it by a constant. And importantly, one of the boundary terms went away. So this term, which Laplacian term, which produced new gradient V squared, we use that the boundary term vanishes. And the reason why it vanishes is because there was no boundary. Okay, so you can repeat this proof for the high regularity. So in Hm-1 works just the same way, except we have to integrate by parts in this term here. And this produces a little bit lower rate. So modulo the rates, this goes just fine for all the way up to HM, and for the HM requires this trick of a smoothie to cover that one too without obtaining any rate. Okay, so that's the case for the domains without boundary. And the above proof does not hold, and actually even the statement does not hold in the case of a bounded domain. When we take, let's say, Dirichlet, classical Dirichlet no-slip boundary conditions. And the difficulty is the mismatch of the boundary conditions for the Navier-Stokes equations. So for the Navier-Stokes equations, we have the no-slip boundary conditions. So the velocity close to the boundary is small, it gets larger as we go here. While for the Navier-Stokes well, for the Euler equations, we have a slip. So there's nothing preventing the velocity to be non-zero close to the boundary. So due to this mismatch, we cannot expect the implicit limit to hold in high regularity spaces. So for the Navier-Stokes equations, as we said, we have a weak solution defined which satisfies the energy inequality. This is actually true in all space dimensions. And since we cannot hope the implicit limit to hold in high regularity spaces, how about in energy? So the question is still reasonable whether the limit holds in L infinity L2. So this kind of picture would allow something like that, because even though the velocities close to the boundary differ, but far away from the boundary, presumably it could happen that we have convergence, and maybe this layer would be small enough to actually expect convergence in L2. And that's the basic implicit limit question. So do solutions of the Navier-Stokes equations converge to the Euler equations in L infinity L2 for t positive? And this is an open problem. So as we said, the answer is affirmative for domains without boundary, but if for the domains with boundary, including when we take just a half space and 2 dimensions, it's open. And as I mentioned, as soon as you require uniform norm, you cannot expect to be true, and it's actually not true. So maybe in L infinity LP, it's reasonable. So in other boundary conditions, other than no slip, there is more hope for the implicit limit to hold. And in fact, it can be proved that, for example, for Navier boundary conditions, the implicit limit holds. So this is the speciality of Navier-Stokes. Also there are limitations about how regular this limit is, but so it's not an easy question either, but at least in this basic form, the answer is yes. So in L infinity L2, the answer for other boundary conditions could be yes, so depending which one. So the basic one of the first papers on the subject was again by Kato, a bit later than the previous one. He proved that the implicit limit holds if and only if the total energy dissipation in a small boundary layer converges to 0. So he did not prove the unconditional result, but that the implicit limits of convergence of the Euler to Navier-Stokes in L infinity L2 holds if and only if you take the domain, and if you compute in this thin boundary layer of size constant times nu, if the total energy dissipation, this is the term you get in the energy inequality, if the total energy dissipation converges to 0, then we have the implicit limit and vice versa. So seems like something should be provable because this layer is very, very thin and maybe just some bounds and the norm is not too high, but that turns out to be a difficult problem. And as Kato said himself, the difficulty is creation of vorticity at the boundary. So presumably something very dramatic can happen, and it does happen. Namely, there is creation of this, and this type of large velocities created close to the boundary actually may perhaps violate this type of limit to hold. So he also proved that the implicit limit holds if and only if we have u of t converging to u bar of t L2 weakly for every individual t, or for almost every individual t. And so this is again bad news, because this means even if we lower the regularity into something weak, like L infinity LP, P small, or some weak limit, that's not going to work, because the weak doesn't work either. if the strong doesn't work. So they're equivalent, and the proof is actually quite easy. So just check this quantity again. Okay, so why doesn't the above proof work? The reason is exactly that dissipation term, which when we integrate by parts, before we only get this term, well, here we get also the boundary term, which is actually of the same order as the leading term, as we well know. So in the heat equation, when we integrate by parts, the terms we're going to get on the boundary are equal order and cannot be absorbed. And actually cannot be controlled either to obtain cutoff result. So he did the following trick. By now, the classical trick of correctors, namely, I'll just sketch, not show the proof, but just sketch the idea. So, for example, for the half space with a similar proof in a bounded domain, you find a corrector which matches the Euler slip. So as we know, the velocity of the Euler is non-negative. So this is U1 bar close to the boundary. And what we do is we introduce a corrector which matches the Euler flows, so that when we add these two things, vanishes on the boundary. And the Euler flow, the vertical component vanishes, so we just make corrector also 0. So we try to design a corrector in a simplest way. So we make it start at the Euler. It has to change sign in order for the second component, which is obtained by integration, to vanish. Otherwise, it's going to be non-vanishing and creates large terms even in the interior. So we need to design a corrector so it vanishes after some point. Let's call it alpha. And so because of this, we need to make the phi1 change sign. So this creates phi2, which is much smaller than phi1, because we are integrating from 0 to alpha. If alpha is small, then phi2 is much smaller than phi1. And so the main corrector is actually the phi1. Then we write the equation for the difference. And so instead of equation for v, we still write the equation for v, but we test it with v minus phi. So we test the equation for the difference for v with v minus phi. And because of this vanishing, now we can integrate by parts and analyze every individual term. The two leading terms compete against each other. So there is one term coming from the linear part and one term coming from the non-linear part. On both, we apply Poincare inequality, or Kato applied Poincare inequality. And the first one required alpha to be large. The second one requires alpha to be small, and they're in balance when alpha is equal to C0 times nu. We can take any constant we like. And that's kind of the proof. So one needs to do all the details, and also he studied weak solutions. So this was quite a hopeful method, because it seemed kind of epsilon close to get the Inviscid limit, but that's not the case. That did not apply Inviscid limit up to now, at least. So there were quite few results on different sufficient conditions for the Inviscid limit to hold. For example, Temam Wang, it's in terms of the tangential component of the gradient. Similarly, this one, Bardos TT, in terms of the boundary integral. There's a lot of results by Kelliher on different aspects of these sufficient conditions. Konstantin Elgin-Dignato Vicol. We also had a result with Peter, Konstantin, and Vlad Vicol for monotone data. So just put it here. So it's one of these where you assume something and then you obtain the Inviscid limit to hold. For example, for the monotone data, these are the ones where U1 bar is positive, so the component is not vanishing. And the sufficient condition is that the vorticity is non-negative. So if that's true, then the vanishing limit holds. Of course, this condition is very reasonable to assume, but this one is a little bit harder to check. Yeah, so it's a sufficient condition. So vorticity non-negative for the Navier Stokes. Okay. There are also unconditional results, and the list is growing, so it's still a quite active problem. So I'll go through these. What is available in terms of unconditional results? So suppose we know something about U0. Can we conclude the Inviscid limit holds? Some additional information on U0, not on the solution itself. The initial result is by Sammartino-Kaflish, who proved that the Inviscid limit holds if the initial data is analytic. And in their proof, the analyticity is y-dy analyticity. So it's an analyticity in an angle. If this is the y variable or x2, so sometimes I write it y, sometimes x2, the analyticity in the angle actually implies the Inviscid limit holding on a time interval independent of the viscosity. And their main tool was Parental expansions. So Parental introduced these expansions in a physical context to describe boundary layers of Inviscid flow. And they used it to actually, they used analyticity to justify the Parental expansion and hence prove the Inviscid limit for the analytic data. That was in '98. Maikava in 2014 proved that the Inviscid limit holds if the vorticity is supported away from the boundary. So if the vorticity has support away from the boundary, so this would still mean that the solution is analytic, but only in a small neighborhood of the boundary. But that was the requirement, that the vorticity support is away from the boundary. Wang, and Zhang proved that Sammartino-Kaflish result using the energy methods. The Sammartino-Kaflish was proven by absolute Cauchy-Kovalevsky theorem. And then Fei Tao Zhang proved a 3D version of Maikava's result. Then in the breakthrough paper, Gwen provided alternative proof of the Sammartino-Kaflish, but without parental correctors by carefully designed norms. And with Vlad Vikol and Fei Wang. Afterwards, we proved that the Inviscid limit holds if the initial data is analytic close to the boundary and Sobolev away. So we only require analyticity here and Sobolev away, which then contains both of these results, because this one is analytic everywhere, and this one implies that the solution is analytic close to the boundary, but it's not the other way around. So this contains both the two results. The Fei Wang proved the 3D version of the same result, that analytic here, Sobolev here. And just last week, Bardos, Gwen, and TT, so that's Trinh and Tuan Gwen, proved the result for the curved domains. So that's a difficult generalization, which shows that even in a curved domain, if the solution is analytic close to the boundary and Sobolev in the interior, then not the solution, the initial data. All these results are about initial data. So if the initial data are such, then the Inviscid limit holds on a time interval independent of the viscosity. Of course, if you allow the interval to depend on viscosity, then the Inviscid limit is true just by Katoff's proof. So just a slight modification. So the difficulties for bigger than t. So in this talk, I'll say a few words about this result, about the Parental expansion, so about Sammartino's result, and then at the end, maybe a little bit more about what is known about Parental, because it's another very interesting subject connected to the Inviscid limit, and of course, interesting in its own right. So the Parental expansions, so first I talk about Parental expansions, and then what's the challenge to actually prove that without Parental expansions. So the Parental expansion was designed by Parental for the following reason. So if one considers Euler equations as a model for fluid dynamics, then one can compute under several assumptions the drag on the body and realize that there is no drag. So it would turn out that it doesn't matter how quickly a body is moving through a fluid, there is no drag or lift, which is counter physics. So therefore, Parental thought that the viscosity should play a critical role in creating, in solving this paradox. And so he designed asymptotic expansion of the Navier-Stokes equations, which then in the close to the boundary, the Navier-Stokes is described by a different equation, which is called the Parental. So I'll not go through the full derivation, but here it's the approach from Sammartino and Kaflish. So if you develop U into a series, so the lowest order term would be Euler, next term would be the adjustment to make the solution 0 and to match first order terms, and then the higher order terms would be of order epsilon. The epsilon is at the moment is an arbitrary parameter, but it turns out it has to be a square root of the viscosity if the viscous terms are to play a role. So the balance of the viscous and nonlinear terms requires epsilon to be square root of nu. And that's the size of the boundary layer. Then the second component of velocity, one can check that it must have epsilon in front in order to preserve the divergence-free condition. So since we are rescaling the second variable, so since the second variable is equal to y over epsilon, that requires this epsilon here in order to preserve the divergence-free. And then cancellation of the terms requires epsilon to be square root of nu, and that this satisfies some kind of equation. The boundary conditions are, so for the Parental we require matchings, same as in cutoff. We want the matching of the slip of the Euler, and this we can require that the Parental is 0. So that's normalizing condition. So if you check what kind of equation this first approximation satisfies, it turns out to be of the following form. Because of this epsilon, in a sense, not precisely that reason, but the equation for the second component actually disappears, and we only get an equation for the first component, which is sort of like heat-like. So we have dt minus dyyy. So there is no dissipation in horizontal, there is only dissipation in the vertical variable. There is some nonlinear terms. And actually, these are linear terms. There's some linear terms, and there is a non-linear terms, which are kind of similar to Navier-Stokes. However, there is no equation for V for the second component, and the second component has to be computed from the boundary condition. So plus dy u. So y is just y divided by epsilon. It's the rescaled variable. So dy, so Vp is equal to 0. So V has to be computed from the first velocity component, and these are Parental-like equations, and by just homogenizing the boundary condition and the boundary. So UP is the U tilde P plus Euler. So just to make it 0, right, to homogenize. And again, the second component being computed from the divergence-free condition, we obtain the classical Parental equations. So the Parental equations read, so we have a heat part, but without dxx. So there's only dissipation in the vertical variable. And and we have nonlinearity, which is similar to Navier-Stokes, and the pressure actually turns out to be given. So the pressure does not cause difficulties as it does in Navier-Stokes. the second component in Parental is computed from the first component from the divergence condition, and this derivative clearly is a problem because there is a loss of derivative in the equation, and as you notice, there is no dissipation. So therefore, this equation looks like it has a one derivative loss. So here we have this VP. There is dx hidden in it. So so the Parental equation has a loss of derivative, and that could explain a lot of difficulties with the Inviscid limit. So the equation which is describing the Navier-Stokes equations in a small boundary layer of size approximately square root of nu is unstable. It actually has a derivative loss. Okay, then Sammartino and Kaflish, they wrote the equation for the error. So you write u as a solution of the Euler plus the Parental-like term plus the error, and the same for the v. Write the equations, and they're quite messy, but they're kind of Navier-Stokes looking. So they have Navier-Stokes-like terms. They also have linear terms, and they also have some complicated forcing terms. Before saying how they further develop, so that they're actually the theorems on that Parental equations cannot hold in, let's say, L infinity. But for the analytic data, they were able to obtain that this Parental expansion indeed holds, namely by writing the equation for the error and then studying it in the analytic spaces. So they wrote the equation for the error, but then even that has to be further developed into the Parental and Euler, and then Parental plus error, and then showing the convergence. So that was their Parental proof. So here I'm going to describe now how to obtain this result with Vlad and Faye assuming the initial data is Sobolev and away from the boundary and analytic close to the boundary. And then I'll say maybe a few more words about Parental at the end. So I'm going to show the proof for the half space, but now the proof works due to result by Bardas, Gwen, and Titi, also for the curve domains. Okay, for the analytic, so the norms, we had two papers. So in the first paper, we used two norms, one which was L infinity based, and the second one which is L1 based. The similar idea was also used in the Gwen, who also used two norms, L infinity and L1. In the second paper, we used the L1 only. So it turns out that L infinity norm is superfluous, and we can actually just work with a L1 type analytic norm. So the important is to design a norm which kind of respects this type of transition from analytic to Sobolev. And of course, the difficulty is that this transition is not sharp. So one needs to design norms which are kind of fuzzy toward the end. There's a kind of supremum going on between on some kind of interval. So we don't have a sharp transition of the norms, at least not the way it is designed, but some kind of more fuzzy way. But in its basic form, the norm is designed as an L1 type norm in a diamond shape region. So what you see here is the y variable for fixed x and for fixed time. So x is fixed. The analyticity in x is done differently, you see in the norm. But in the y variable, it's a diamond shape. And instead of measuring the supremum of the analytic function, we rather look at the L1 norm over this kind of broken paths. So we take the supremum over all broken paths between 0 and 1 plus mu. And mu is a parameter which varies in the norm. So the complex weighted L1 norm is defined as the supremum of L1 among all the paths going from here to there. And then this is in the y variable, and then to do analyticity in the x variable, we use the Gevrey idea, which was originally by Foyash and Temam. In the L2 setting, there is also L1 settings, and also Sammartino-Kaflich. They use partial Fourier transform in the x variable to study analyticity. The exponential decay of the Fourier coefficients implies analyticity, and it's in fact equivalent to analyticity. So the analyticity radius in the x variables, it's also decaying to 0 as you approach the end of the analytic domain, but it's uniform up to the boundary. So if you look at the analyticity in x, it's uniform up to the way it's written, it's 1 plus mu minus real part, so it's like this. So it starts with 1 plus mu close to the boundary, and then it vanishes at 1 plus mu. So that's the analyticity in x, and this is the analyticity in y. And the norm, precisely, we also have to take derivatives up to order 2, and the second order requires a weight for technical reasons. So this type of thing measures the size of the analytic norm, and it has to be incorporated to at the end to close the estimates. So this type of norms, as I mentioned before, they do not control the size of the solutions. It's not like, okay, size is small, so the Inviscid limit holds, but it allows growth of the functions. So the functions can in principle still grow like 1 over y, 1 minus delta. They just have to be integrable. And yeah, we have y dy analyticity. For the Sobolev part, we just use the weighted L2 norm, and the total norm is then the sum of the Sobolev norm and is the sum of the Sobolev norm plus the analytic norm. So the Sobolev norm also we have to take derivatives up to order 3, which then requires initial data to be at least H4 regularity. And then, so this is the precise result. So if the omega naught satisfies H4 in the Sobolev region away from the boundary, and a second derivative being in that analytic space described before, then the total norm, so Sobolev plus analytic, is bounded by a multiple of this norm. So this triple norm, it's as I wrote before, is the sum of the analytic and Sobolev. So once you have that, then by the cutoff result, the Inviscid limit then holds. So if omega naught is analytic, or more precisely satisfies these assumptions, analytic close to the boundary in this sense, and Sobolev away from the boundary in this sense, then the lim sup on some positive interval of time, depending on these norms at the beginning, then vanishes in the limit. I will not go, I will just show you some basic thing and the strategy of the proof, but I will not sketch the proof. So I'll maybe just have a glance of how cutoff criteria comes into play to show the Inviscid limit, and then just some ideas to how to close the estimates in these analytic spaces. Okay, so to check the cutoff criteria, so once we have the uniform bound as here, then we need to obtain the L infinity bound for the omega. So this is obtained from the mild formulation about which I'll talk in a moment. So once we have the L1 bar, the L infinity bound is 1 over square root of nu t, which even though it's a bit large, it allows the vanishing limit to holds. So this is the cutoff quantity, except that we are actually going all the way to infinity. So we don't have to even take the small layer around around 0, around the boundary. So we go to the verticity. We split into the part close to the boundary and away from the boundary. Close to the boundary, we split omega squared into L infinity part. So we just bound one of the omegas by the L infinity norm. And the second one, it's actually under control because we have subole uniform bound. So this term is actually going to 0. We don't have to look at it anymore. So the term away from the boundary is going to 0. So we just need to look at this one. So L1 norm, it's precisely what we are bounding because we have L1 norm in the y plane. So we can just bound it by inserting those exponentials. And then we just get 1 over the square root of nu s. And nu partially cancels, but it's still square root of nu left. So the cutoff quantity, so the total energy dissipation in the whole plane is bounded by the square root of nu, implying the Inviscid limit in the L infinity L2 topology. Not stronger than that. So you can go the way you can do L infinity LQ as well as done in other papers. So verticity formulation in the half space. So the basic important device is due to Maekawa, which writes the Navier-Stokes equations in terms of the verticity. Of course, in a bounded domain, the difficulty is that the boundary condition is not very simple. It's not omega equals 0 like it would be for Navier-Stokes. So we don't have omega 0. Instead, we have a more complicated boundary condition, which is Neumann-like. So without this term, that would be like a Neumann condition on omega, which is something to do with a nonlinear part. So this represents the inverse Dirichlet Laplacian and dy at the boundary. There is a short derivation of this, but I'll not go through it. But that's now well accepted and useful curl formulation for the Navier-Stokes equation in a bounded domain. Its advantage is that there is no pressure. Disadvantage is that the conditions are kind of non-homogeneous and non-linear, but probably non-homogeneity is more of a problem. Okay, so this boundary conditions is obtained from the D2U1. So I'll just say this, and then using the BSO1 law. Then we have the integral representation of the solution due to Tuan and Trinken-Guen, which writes the verticity equation in this form. So dt omega minus nu Laplacian omega is equal to n, and Neumann-like boundary condition is B. Both of them are nonlinearity, like U grad omega, essentially. And using the Green's function, we can write this in the mild form, partially Fourier transformed in the x variable. So this is the starting point, is to study the mild formulation of the Navier-Stokes equation using the Green's function for the Maekawa boundary conditions. And the important tool is the result by Guen and Guen, which writes the Green's function as a sum of two. One of them is the Neumann boundary condition kernel. So they're just a normal Neumann Green's function plus a residual term, which is not lower order, but does not contain time. So it's kind of the same size, but it contains does not contain time. While the second part is kind of in the spirit of the this Neumann heat kernel. So we have upper bounds for the kernel, and now we need to design a strategy to close these equations in the norms provided. I will not go through the proof, but just sketch what one needs to do. So first one proves the y-analytic norm estimates of this. So the idea is when you have integrals from 0 to infinity, you split them into integrals in the analytic regions plus the analyticity in the region away. So you split this into two parts. In one, you use the analytic bound, L1 analytic bound, and in the other one, use the sublime bounds. Then we need to bound the norms of n, for which we use the Biot-Savart laws. So because nu contains u and gradient omega, after getting away from gradient, you have u times omega. Here you put L1 norm, here you put L infinity norm. And this we use Biot-Savart. So use the Biot-Savart law to bound the nonlinearity in terms of the square of the omega in L1. That's for the analytic region. For the sublime region, we do energy estimates. So the localized energy estimates produce some boundary terms. And in this intersection of these domains, you use the analytic estimates. And then you just put the bounds together. Yeah, so since I'm approaching, I think, the end of the time, I'll just kind of go toward the closure. So we have the more recent result with Trinh Nguyen, Vlad Vikol, and Fei Wang on the validity of the Parental expansions in the half space. Namely, we proved that the Navier-Stokes equations are well approximated by the Euler equations and the Parental equations through the verticity formulation and in these L1 norms, which we described, and the order of the approximation is c times square root of nu. So this has a bit longer proof. Yeah, so omega p, this is the Parental verticity. I meant to talk a bit about the Parental equations also, but maybe that's for another time. So it was more like just in case so perhaps this is a good place to stop. So thank you very much.